All right, good morning. So my name is Denis Defrère. I work at KU Leuven, and we are just starting a new project, a new ERC project, which is called SCIFY, for self-calibrated interferometry for exoplanet spectroscopy. And within this project, we will build a new infrared imager for the VLTI. So it's an interferometric instrument for the VLTI. There are different collaborators to this project. So ANU, CSL Liège, Zurich, University of Arizona, Cologne, University of Liège, IPA Grenoble, ISO, also in NASA, collaborators on nulling, and l'Observatoire de Nice. So let me first introduce the science motivation for this project. We have already seen this picture this week. This is a typical picture that you can take of a different distant planetary system with an 8-meter class telescope. You can see the 4 giant exoplanets of the HR8799 system on this image. And this is a typical picture that we can take. So that's giant exoplanets which are beyond the snow line of the system. And the detection rate for the system is really small. It's less than 1%. Recently, there is a new paradigm to characterize these systems. We've seen that last year with the gravity instrument. We can take really precise spectra using interferometry. For the first time, we can characterize exoplanets. This has been demonstrated by the gravity team. You can see the spectrum here on the top right plot of HR8799e, which is the inner planet. And it's really really good data set, 5 times more precise photometry than with single dish telescopes, and also an extreme astrometric precision of 40 microarcseconds. Also with gravity this year, there has been the first direct observation of a planet which has been detected by RV. So the first imaging of such a planet, and also with a really good photometric accuracy and astrometric precision. You can see here the spectrum of beta peak C in this case, also with gravity. So we want to characterize more of these planets now, and the question is how to do that. We know that most of the exoplanets are located within the snow line. So if I go back to this image here of HR8799 system, we know that most of these planets are located within the snow line. So this is this green region that you see now on the left image. And if you look at the usual exoplanet plot, so Mars versus period, that's all these planets which are in red, radial velocity planets. So how can we push the detections to these really small inner working angles? And in order to do that, we need more angular resolution. We need larger telescopes. So I stole the table from Bernard about all these infrared imager, and so we need a larger telescopes. So we have in orange at the bottom of the plot the larger ones. There is the LVTI in FISO mode, but there is also obviously the ELT coming, and METIS will obviously discover and characterize a lot of these exoplanets. But if you want to go one step further and really go within the snow line for the planet forming region, we need an even larger telescope. And for that, we have the VLTI. And so you can see on the left, the array, which is covered by the ELTs in red, compared to the ELT primary mirror. And so there is a discovery space here that will not be covered by the ELT for the highest spatial resolution. Obviously not the same sensitivity as the ELT. So it's a complementary discovery space. And this is what we want to do with the SCIFY project. So it's a new ERC project, which has been just been started last week. And the goal is to build a dedicated high contrast interferometric instrument for the VLTI. So at L band will be the visitor focus. So currently there is the MATIS instrument already working at this band on the VLTI, but it's not optimized for high contrast observations. It's characterized for imaging at spectral resolution. And so really with the SCIFY project, we want to leverage the amazing VLTI infrastructure for doing interferometry, and also the upcoming upgrades for Gravity Plus, and also leverage the progress in nulling interferometry, mostly achieved in the US. So right now there is no nulling instrument on the VLTI. There has never been one. And the past 20 years, there has been a lot of progress in the US. And we have seen a lot of exciting results from the LBTI this week. But I can also mention the Glint instrument and the Palomar fiber nuller and Keck nuller. And also we have been doing a lot of progress in self-calibration approach. So the way to obtain and reduce the data has greatly improved and really helped to get the highest contrast possible. And we can now tackle the exoplanet contrast regime. So to showcase the progress in nulling interferometry, I like to come back to this plot that has been shown by Steve Hertel on Tuesday. What you can see here is the sensitivity in ZODI, meaning that 1 ZODI is the brightness of the zodiacal disk in the solar system for different instruments. And you can see in the yellow histogram is the space instrument. It's WISE, and the sensitivity is typically 1000 ZODI. So 1000 times the brightness of the solar zodiacal cloud. With the Keck nuller, the first generation, or I would say the second generation nulling instrument, we gain almost 1 order of magnitude in sensitivity, even compared to space instrument, because you can resolve the disk from the star. And then with the third generation nulling instrument like the LBTI, again, more progress, especially on the data reduction side and sensitivity of the LBTI, allowed to go even deeper in contrast, so almost 2 order of magnitudes compared to space instruments, and almost getting down to 1 ZODI in this case. And we know what are the main limitations of these instruments. So we know for the near-infrared instrument, like the Palomar fiber nuller, we are limited by the high frequency phase jitter. And within SCIFY, we will look into that. We will look into how to improve the OPD stability of the VLTI and reduce the high frequency phase jitter. That's one of the work package of SCIFY. And we know for the mid-infrared nulling instruments like the Keck and LBTI, we are limited by background and detector systematics. And we will also look into that for with a work package in SCIFY.
1 minute, please.
Excuse me?
1 minute, please.
Okay. I like also to show this plot about the probability of detection of forming exoplanets in planet forming region. So this is for a system here at 130 parsecs. You can see the probability for different instruments as a function of time since disk dissipation. And you can see that really the VLTI, this is the blue curve, the highest curve here on the AT, has a higher probability of detection than even METIS for this particular case. And really the main reason is because we need the angular resolution to go really within the snow line of this planet forming region. I would like also to finish by saying that we are also with SCIFY preparing a mission like LIFE, which is a nulling instrument for space that has been submitted to ESA. And with LIFE, the goal is to go after rocky exoplanets, to go to space, to have the sensitivity to do the same kind of observations, but with a much better sensitivity and be able to resolve the habitable zone around nearby stars and characterize rocky exoplanets. So this is the LIFE space mission. And to conclude, I would like to mention that we have 2 workshops in early December. One on LIFE, this is the 3rd LIFE workshop, so November 30 and December 1st. That will be online. And then the following 2 days, we have the SCIFY workshop 1. So if you're interested, you can scan the QR code and register or talk to me. Thank you.
Okay, thank you very much. Thanks for the update. So I want to check if there are any questions on Slack. So far, I don't see anything. In case someone has a question, please post it or raise your hand here. But I can ask a small question. Maybe I missed it, sorry. At which stage is this project now? I mean, the SCIFY? Is it in the design?
So the RC is just starting last week. So we have a timeline to deliver the instrument within the duration of the RC project. And start commissioning the instrument within the RC project. So we are currently assembling the team, defining the work package and working on the design and ordering the long lead items and that's the beginning.